So the next vignette I'll share with you is on material fatigue and anterior cruciate ligament failure. And this has been another very exciting application of the AFM-IR technique. This collaboration has been across 4 universities spanning the globe. And so the team comes with Steve Schlecht at the University of Indiana, with Ed Vodes, our ACL surgeon, and James Ashton Miller, Melanie Below, and So-Young Bach at the University of Michigan in sports medicine and mechanical engineering. Also from Michigan Chemistry, where Jinhee Kim and Junji Chen worked on the problem. And at Monash University in Australia, myself, Kevin Tara, and Jinhee, and then now myself at UAB. So why are we bothering to study ACL injury? What's going on? Well, there's been a 400% increase in about 20 years of ACL failures. And so this is remarkable. It's a really big problem. What's going on? And the other reason we really want to look at this is that a lot of the patients are a result of sports participation, and many of them are quite young. Many of them are under 20 years old. So it's a very fast-growing injured population. And here's the other really big concern. Young women particularly are having their ACLs fail, and maybe in their teen years. And if they have that failure in their teen years and get the surgery, it can fix the immediate problem, but they're 80% chance likely to develop osteoarthritis in that knee within 10 years. So then they're into their mid-20s and are already suffering from osteoarthritis in their knees. So this is a major problem that we would like to avoid. One of the interesting pieces of this is that 75% roughly of all these injuries are what we call non-contact injuries. Sometimes we think about knee failures, ACL failures in the knees as arising from a very violent tackle in football or soccer, and that certainly occurs. But in fact, it's much more common that the athlete is simply running on the court or the field, maybe changes directions, does a cut, and then their knee fails, even though they've done that same motion thousands of times in the same way with no failure. So we'd like to understand what's going on with that. So this all came about because ACL surgeon Ed Vodes reached out to me and said, could you help us understand what's going on with the materials changes occurring in the ligament that might lead to this failure? He and James Ashton Miller and Melanie Beloy had come up with a hypothesis that the ACL ligament material was undergoing a classic material fatigue process such that the ligament failed under a normal mechanical force. In other words, that's the 75% chance of failure. You can see James's really interesting machine where he takes whole human knees and puts them in this machine, applies a 4 times body weight force, including limited knee rotation to mimic a pivot landing like you'd have in sports and a common failure, to cause that material fatigue. And so what we're able to do is from Ed Vodes, we were getting patient samples that we could look at where people's ACLs had failed, and we're getting cadaver-based samples where we can have a controlled forces that have been applied to the materials. And Dr. Vodes came to me actually just after I'd gotten our nanoIR 2 delivered, and I said, wow, well, this is interesting. Let's take a look, see what we can see. Now, one of the interesting pieces about trying to understand and study anterior cruciate ligaments is they have this really fascinating hierarchical structure that requires multiple approaches to try to understand what's going on, from molecular to nanoscale to microscale. Guattari published this really beautiful version of what this looks like, from the amino acids, the collagen molecule, to the collagen fibril, to the fiber, to the whole tissue construct, back in Nano Letters in 2011. And when we thought about this problem for Dr. Vodes, we said, wow, you know, AFM-IR seems really interesting here because it can measure the protein present, the collagen. It can measure the presence of mineral. we thought it could maybe look at disorder or order questions in the collagen as well and get us topography. There's another aspect of AFM-IR that is really important for this sort of tissue study. That is, AFM-IR can measure fully hydrated tissue. And so this is something that's quite different from classical IR microscopy. In classical IR microscopy, you take thin sections and typically dry them such that you can push the infrared light through and do an absorption measurement. But of course, drying the section out has profound effects to the secondary, tertiary structures of the proteins present in that tissue. With AFM-IR, we are able to do cryotoned, fully hydrated tissue measurements. So this is really a game changer for thinking about the use of infrared with respect to biological tissue. Of course, AFM-IR also has fantastic aerial resolution. In our nanoIR 2 days, with about 50 nanometers, the machines today, of course, can push up to 10 nanometers XY resolution, perhaps better. The other interesting piece is we can get simultaneous acquisition of relative stiffness data using that PLL frequency that Jenny described earlier. That we get along with the infrared data and the topography data. So let's look what we can do with all of these things to try to answer some interesting questions here. So how does the sample preparation work?